Okay, we've got another integral on the board from the MIT 2022 integration bee. This is problem number 8. Even though this seems to be a pretty straightforward problem, I actually found this one to be one of the more interesting problems just for me personally. So let's get started. What I'm going to do is we're going to solve this by two different methods. Method 1, we're going to do a u substitution. I've done, I think in a previous video, I had one very similar to this, where if we make our substitution u equals x squared, this is going to simplify our denominator into something with a square, which usually helps. And then let's just look, our du is going to be 2x dx. So we can actually, let's just create a 2 here and a half, and that's going to set up our u substitution nicely. Then here you'll see I've made the substitution. We just have du over 1 minus u squared. And then what we can do here is this is actually just a common integral that we don't really have to do any work on. This is going to be hyperbolic tangent inverse of u plus c. We'll do our back substitution. We're going to have for an answer hyperbolic inverse x squared plus c. And this is our answer, and this is actually okay, but there's a couple problems. First of all, this is kind of too short of a video. And this is actually a valid solution, but the only thing is it doesn't actually match what they have in the answer key for the MIT integration bee. So I think what we're going to do is let's go on to method 2 and see if we can get some more information. Okay, so now I have our answer for method 1 over on the right, and then we're going to do our method 2 here. I'm just going to use the same u substitution I did in the first method, and then we have our integral with our substitution in this form here, du over 1 minus u squared. Then what I can do is factor the denominator here as 1 plus u, 1 minus u, and that's going to set us up for partial fractions. Okay, so you'll see that I've just taken here on the left and rewritten what we had inside the integral. And then what we're going to do is equate this to splitting this up into two fractions, and then we just need to solve for this unknown a and this unknown b, and then we're going to have a way to break this integral into two easy pieces. And we could use the cover-up method, but actually I'm not going to do that here. What I'm going to do is we can multiply here by 1 plus u over 1 plus u, or multiplying by 1, and we can do basically the same thing over here, multiplying by 1 minus u, and then we can actually just solve for our coefficients, equating it to this 1 right here. So now what I've done is I've just taken our numerator here, this whole thing, and I have my a times 1 minus u, b times 1 plus u, equating it to this 1 right here, and then I distributed in the a, so we have a minus au plus bu, and I actually plugged in the 0u here so that we're going to equate our coefficients so we can solve for our a and b. Then over here on the right, you'll notice that I separated out our u terms, our terms with a u in them, and just the constant terms. So then we just have a system of two equations and two unknowns, and we can solve that. And what I'll do is I can just skip to the solution for this, but it's going to be a equals 1/2. And then you'll see if you plug in a half in here, b has to be 1/2. And you'll notice that'll also work for our first equation. If we subtract a b 1/2 minus a half here, that's going to give us our 0. So we've solved for our a and b values. Okay, so now we've broken this into two integrals, and we have our a value that we found in the previous, from our partial fractions, we found this a value, and then we also found this b value that was each a half. And so now we're ready to integrate. Now first we can multiply this half and half, and we're going to have 1/4. And the integral of 1 over 1 plus u is just ln absolute value 1 plus u. But you know what? We're going to drop the absolute value because MIT integration b doesn't require it. And then multiplying those halves together, we're going to have 1/4 ln 1 minus u plus c. But we don't want to forget we got a minus sign there. That's actually, I kind of make that mistake a lot. So that we have to bring that out, because if we did another like quick u substitution, there would be a minus. So let's just fix. So we're going to bring this minus sign out and have it right there. And then we can factor out a 1/4, and then property of logarithms, when we have a subtraction, we can write this as a division. So we can write this as 1 plus u over 1 minus u plus c. And at this point, we can just factor out a 1/4 in front, and then we'll use our minus sign with the property of natural log, or any log, and we can write this as a division. So we'll write it as 1 plus u over 1 minus u plus c. Then we'll just do our back substitution here. And so we're left with, for our answer, 1/4 ln 1 plus x squared, 1 minus x squared, plus c, and we're done. So that's our solution in the second method. And now this actually is the exact answer that they have in the solutions for the MIT integration bee. So this answer is correct, but what about our answer from the first method? Well, it turns out that these are actually the same thing. So this is equal to this. Let's just see if we can show how that's true. So we have this identity on the board for inverse hyperbolic tangent, half ln 1 plus x, 1 minus x. You'll notice if you multiply this by the half here, you get the quarter. And then you notice if you input x squared, you get back the exact same thing, 1 plus x squared, 1 minus x squared. So just doing the substitute, just using this tool, you'll see that we can convert this real quick from here to here. So it's pretty clear that this tool here will get us to the correct solution. The only question you might have now is where did this formula come from? So let's show that real quick. Okay, so now we just want to show that the inverse hyperbolic tangent of x is the same thing as half ln 1 plus x, 1 minus x. What I'm going to do is let's equate this to a y so that we can use our invert this. So we'll just look at this piece, and we want to show that our y equals this. So then using our inverse, we can rewrite this as x equals hyperbolic tangent of y. And then we can use our definition of the hyperbolic functions. So we can rewrite our expression here as e to the y minus e to the negative y over e to the y plus e to the negative y. And that's going to be the same thing as our hyperbolic tangent. You could also do it with hyperbolic sine and cosine, and you'd have the 2's in the denominator that cancel. We're just going to skip to this piece. Then to simplify this a little bit, we'll multiply top and bottom by e to the y over e to the y, and we're going to have e2y minus 1 over e2y plus 1 equals x. Then we can multiply this part over to the left. And then remember, at this stage, what we want to do, we need to isolate our y, because we're trying to show that y is equal to this expression on the right here. So let's get all of our expressions with y on one side. So we'll subtract this over here, and we'll bring our x over here, and we'll do this in one step. Okay, so we've rearranged this. Now let's factor out an e to the 2y. So we'll have e to the 2y, x minus 1 equals minus 1 minus x. Then I'm just going to divide an x minus 1 on both sides here. But then you know what I'll do? Let's change the sign here, and then we can change the sign here. And then so this will cancel, and we rewrite this as e to the 2y, 1 plus x over 1 minus x. We'll take natural log on both sides, natural log here, and you can see it's getting close. Our natural log with an e is going to cancel, and we're going to have, but from here all we need to do is divide 2 on both sides, and then we're left with y equals 1/2 natural log 1 plus x over 1 minus x. And this is exactly what we wanted to show, because this is the same thing right here. So we've shown our little tool that allows these two methods to be actually the same thing.